In this section, we are going to study covalent bonding. And as you recall, covalent bonding refers to the sharing of valence electrons to form a chemical bond. So by the end of this lesson, you should be able to describe what a covalent bond is, know the difference between a single bond, a double bond, and a triple bond, determine bonding capacity, and then we'll do a lesson on drawing Lewis structures and structural diagrams for molecules. So let's get into it. Recall that compounds can be divided into two categories. So we can have ionic compounds. And remember, those are compounds where the bonds are formed from a positive ion and a negative ion. That force of attraction causes them to bond between the positive ion and the negative ion. And then there are molecular compounds. And molecular compounds, they don't have that transfer of electrons. What they do is they share their valence electrons to form a bond. So here we define what a molecule is, and this is a very important definition. You should definitely be able to finish grade 11 chemistry and define what a molecule is. So I'll put a little big star behind there, a little star there. A molecule or molecules are composed of two or more atoms that have covalent bonds with each other. Okay, so these are particles made up of atoms that are bonded using covalent bonds. So an example of that would be like water. Water is a particle. It's a molecule. It's made up of oxygen and two hydrogen atoms that have bonded together through the sharing of electrons. Another example of a molecule would be natural gas, so CH4, which you may recall from previous years, the name of which is methane. Okay, so this is methane, this is natural gas. It is sometimes used to heat homes or also in natural gas plants to burn and provide electricity. So this right here is also called a molecule because it is made of atoms that are sharing valence electrons to make a single particle. Okay, so that's what a molecule is. Diatomic molecules, okay, simply mean molecules that have two atoms. So an example of a diatomic molecule could be, for example, hydrogen chloride, right? That's a diatomic molecule because it is made up of two atoms, diatomic. There are also things called diatomic elements, and those are the elements that we previously studied and that you've studied in other years. I call them Hofbrinkel because that name sort of sticks out in my head. These are diatomic elements because these are elements that are made up of two atoms. Okay, so they're found in nature, bonded to themselves, and there's two atoms each. Okay. Polyatomic molecules, however, are things with more than two atoms. So more than two atoms. Right? So a polyatomic molecule could be like, for example, glucose, which is sugar. Right? As you can see, it's made up of three types of atoms, but altogether 24 atoms in total that are bonded together to make the molecule of glucose. And there are lots of complicated polyatomic molecules as well as simple ones as well. So the key idea here is to distinguish between diatomic, having two atoms, like hydrogen chloride. Hydrogen fluoride would be another example, right? And also polyatomic molecules, which are made up of more than two atoms. How is a covalent bond formed? Well, in covalent bonding, atoms no longer give up electrons like they did in ionic bonds, but they share them, as we previously said, to obtain a stable octet. These are mostly nonmetals. Nonmetals predominantly form covalent bonds, whereas metals and nonmetals, for the most part, make ionic bonds. covalent bonds are generally formed from nonmetals, or formed by nonmetals. Electrons are attracted to both nuclei and shared between them. So I'm just going to show this once as a Bohr-Rutherford diagram. If we take a look at fluorine, and for the sake of this, I'm just going to include the protons. So I have one atom of fluorine here with its nucleus and 9 protons. Its inner shell has 2 electrons, but its outer shell has 7 electrons. So 2, 4, 6, and 7. Remember that elements strive to complete their outer shells for chemical stability. So a fluorine atom is quite unstable because it doesn't have a full outer shell. So it could either take an electron from another element, and so that would produce an ionic bond, or if there was another element that had one electron to share, it could form what's called a covalent bond. So in this case, if we had another fluorine right beside it, its inner shell has 2 electrons, and then its outer shell has 7 electrons. Right? I'm sorry for the lopsided drawing, but it's got 2, 4, and 6. But that 7th electron now is going to be shared with this other fluorine atom, and now these 2 electrons are being shared between the 2 atoms. This is your covalent bond. Because they are co-sharing their valence electrons to complete their outer shells. As you can see now, this has a full outer shell, and this one has a full outer shell by virtue of them sharing their outer shell electrons. In Lewis structures, this is these Bohr-Rutherford structures. They can be pretty cumbersome to draw, so we often just will draw like a Lewis structure. And so in a Lewis structure, we just do, for example, we do the fluorine here. We show its valence electrons, right? And then we show the 2 electrons bonded together as represented by a dash. So this dash represents the 2 shared electrons. You will also see some notations are done this way as well, where the 2 shared electrons are just drawn as circles between the 2 atoms. But more often than not, to keep things a little cleaner, the dash is used to represent the 2 shared electrons in the covalent bond. The electrons that surround these atoms, so these electrons that were not involved in bonding, these are called lone pairs. Those are lone pairs of electrons. Those were not involved in bonding. Okay. So we'll write over here, lone pairs are electrons that are not used in bonding. And as we can see here, fluorine has 1, 2, 3 lone pairs, and this fluorine had 1, 2, 3 lone pairs. Those weren't at all involved in bonding because they were already paired up. If you leave out the lone pairs, you are left with what's called a structural formula. So this F bonded to F is a structural formula. So if we were to look at the reaction that forms bromine, well, we'll see that bromine right here has 2, 4, 6, 7 valence electrons, and we have a bromine here, 2, 4, 6, 7, right? What they will do is they will share these valence electrons here, and this will form a covalent bond, and we will end up with a bromine molecule. And again, it's a molecule because it is a particle made up of two atoms that are bonded together in a covalent bond, right? Those are the shared electrons. Notice again that bromine has these lone pairs here that were not involved in chemical bonding. So that, I just drew the Lewis structure, and the structural formula is quite simple. It's just without the lone pairs. And that's your bromine. That's the structural formula. So this is Lewis structure. Alternatively, this is a Lewis structure as well. And this is your structural formula. Okay, moving down. Covalent bonds can also be double bonds or triple bonds, right? So if you have double bonds, then you don't just have one pair of electrons being shared, you have two pairs of electrons being shared for a total of 4 shared electrons. In a triple bond, you have 3 pairs of electrons for a total of 6 shared electrons. And quadruple bonds do not exist, at least for the purposes of this course. We're not going to look at quadruple bonds. All right, so how do we do a double bond? Let's look at 2 oxygen atoms. So we have an oxygen atom here with 2, 4, and then we have the 6 electrons. These ones are unpaired. And we have an oxygen here, same idea. What will happen here is that these 2 electrons will come together to form a covalent bond, and these 2 electrons will come together to form a covalent bond. And what we end up with is we end up with an oxygen that has made a double bond with another oxygen atom. Now, if you want to be technically correct, because these are electrons and these are electrons, electrons all repel each other. So we would generally write them like this, actually, on an angle, to show that they are repelled from each other, right? They're all repelled from each other, and in fact at approximately 120 degrees from each other. But this is acceptable as well, at least in grade 11. If we look at a triple bond would be something like this. Well, we have nitrogen here with its 3 electrons. We have nitrogen here with its 3 unpaired electrons. These are your lone pairs. Remember, these are not involved in bonding. So we'll form a bond here, and then we'll form a bond here. And then these electrons as well will form a bond. So we will have 1, 2, 3 electrons, or 3 electron pairs. And so we would actually write this like this: 1, 2, 3, nitrogen. And just to be thorough, I'm going to move these pairs to the side so that we show the maximum repulsion. Right, or they're moved here to minimize repulsion, but yes, this is where they should be located, to minimize repulsions between the two, because they are in fact repelling each other. All right, so bonding capacity. Bonding capacity refers to the number of covalent bonds, the number of shared electron pairs that an atom can form. So if we look at hydrogen, I'll draw hydrogen like this. It has 1 valence electron. It has 1 unpaired valence electron, so it has 1 bonding electron, so therefore its bonding capacity is 1. If we look at carbon, carbon has 1, 2, 3, 4. It has 4 valence electrons. Each of these electrons here can form a bond, so we have 4 bonding electrons, and it has a bonding capacity of 4. With nitrogen, nitrogen has 5 valence electrons. However, it has a lone pair right here, so we only have 3 bonding electrons and a bonding capacity of 3. Oxygen has 2 bonding electrons, but it has a total of 6 valence electrons. So oxygen's bonding capacity is 2. If we look at the halogens, I'll just represent the halogens as X because it could be any one of those. Halogens are written with 7 valence electrons, but only one of those electrons can form a bond, so therefore it has a bonding capacity. It is capable of making one bond. If we look at silicon, silicon is 1, 2, 3, 4, 4 valence electrons, 4 bonding electrons, a bonding capacity of 4. If we look at phosphorus, phosphorus has 5 valence electrons, 3 bonding electrons, and a bonding capacity of 3. Sulfur, 6 valence electrons, 2 bonding electrons, and a bonding capacity of 2. So if we take a look here, it asks which elements had the highest bonding capacity. The highest bonding capacities that we see here are silicon and carbon. So carbon and silicon have the highest bonding capacities. And which element has the lowest bonding capacity? So if we look at the elements with the lowest bonding capacity, that would be our hydrogen and our halogens. So hydrogen and the halogens have the lowest bonding capacity. There's one exception that we do need to take a look at here, and that is boron. So if we take a look at boron, boron is written like this, and typically has a bonding capacity of 3. So it will only make 3 bonds. Okay, so let's take a look at what we've looked at so far. Go back to the learning expectations. Okay. We looked at the 2 types of compounds, ionic and molecular. We defined what molecules were. We showed how covalent bonds form with the sharing of electrons. We did a brief introduction to Lewis structures and structural formulas. We talked about double bonds and triple bonds. And then we also looked at bonding capacity for individual atoms, right? And again, bonding capacity refers to the number of covalent bonds that an atom can form. And so we look at the number of unpaired electrons, and that is our bonding capacity. Because as you will recall, atoms with lone pairs are not involved in chemical bonding. Thanks for watching.